Hello everyone, this is Justin. I hope you guys are all doing very well. Today I'll go ahead and walk you guys through chapter 13, practice problems number 1, questions through 1 through 4. And like always, if you have any questions regarding my walkthrough steps and processes, just feel free to contact me or you can contact any of us as well. So for question number 1, it's asking us, two wizards sit on the opposite side of the playground seesaw. If Harry, weighing at 215 newtons, is 1.8 meters from the seesaw axis of rotation, and Ron, weighing at 174 newtons, is 1.9 meters from the axis of rotation, what are the torques created by Harry and Ron? Which end of the seesaw will drop? So this question is asking us two things. What are the torques created by Harry and Ron? On top of that, it's also asking us which end of the seesaw is going to drop. So if we go look back what the equation is for torque, we know the equation for torque is basically torque is equal to force times distance. So just write it up here. So in this case here, we are given the force and distance from both individuals here. So we look at Harry is put at his force is 215 newtons and his distance is 1.8 meters. And then same thing with Ron, his force is 174 newtons and then his distance is 1.9. So we're already given everything that we really need to find their total force. So in this case here, we just basically plug it into our equation. So for Harry, we're just gonna use T is equal to 215 newtons, we said, times 1.8 meters. Which would give us an answer of 387 Newton meters. And then for Ron, same process, we just plug it into our equation to what's already known. So his force is 174 newtons. And then we see his distance from the axis of rotation being 1.9. So not a big difference in the distance, but we do see a huge difference in their in the force. So in this case here, we do see the final answer being 330.6 Newton meters. So in this case here, we obviously see a big difference at the end of the torque from both individuals here. We see a greater torque being produced from Harry, which is this top one right here. So in this case here, since Harry's is greater than Ron's, we can just go ahead and conclude that the seesaw will drop on Harry's side, since we know that this one is greater than the bottom one right here for Ron. So in the case here, since Harry's T is greater than Ron's T, Harry's and the other seesaw will drop. So yeah, that is the answer for question number 1. So you first started off by getting what are the torques created by both Harry and Ron, so both individuals, and we were doing that by whatever was already given. And then at the end, we just basically see which torque produces more, and then at the end, we just can conclude that since it is greater, we know that it'll be dropping at that side. So that's going to be the answer for question number 1. All right, so moving on to question number 2. This one is asking us how much force must be produced by the biceps brachii at a perpendicular distance of 3 centimeters from the axis of rotation at the elbow to support a weight of 200 newtons at a perpendicular distance of 25 centimeters from the elbow. So in this case here, it is asking us at first thing first. It's already at the first part of the question. It's already asking us what we need to find here. So in this case here, our end goal is to find how much force is produced by the biceps brachii. and then everything else we are already given. So in this case here, we're talking about our leverage systems here. So let's just start off by basically writing down what we do know already. So what our known is. So what's known? So in this case here, we do have the distance of the muscles, which is our biceps brachii. So the distance for this one, and then remember for the plug-in equations, we don't want to keep them in centimeters. We always want to change them to meters. So in this case here, 3 centimeters converted to newtons, which is be 0.03 meters. And then afterwards, we aren't giving the force of the muscle, so that is what we're going to be finding here today. So let's just go ahead and write this down as well. We're also giving the distance of the weight. So it can be written down like this. And then this one is telling us that it's 25 centimeters from the elbow. So if we just convert that to meters, that would just be 0.25 meters. And as well as we are giving the force of the weight in newtons. So in this case here, the force of the weight in newtons was indicated at 200 newtons. And then another important thing that we want to know, even though it doesn't simplify that it's negative 200 newtons, but we can infer that it is negative 200 newtons. The reason why towards this is we put a negative there just to imply that the force of the weight is acting downwards. And since we have that state of static equilibrium trying to like support the weight, that one is going to be negative. So we just want to keep that in mind here. And then that brings me to my next point here. The sum of torque would be at 0. Why do we say this is at 0 here? So we know, since like I mentioned earlier, since we know that we're supporting this weight, aka being in that static equilibrium, this just basically implies that the weight we're holding is not moving. So in this case here, we would have the sum of all torques being at 0. So that's why we would put that there. So now we just basically plug this into our formula. So basically it would just be the sum of torque, which would equal to the force times distance of 1. So in this case here would be the muscle. And then adding it to the force of the other thing. So in this case here, it would just be the weight. So force of weight times distance of weight. And then we just simply just plug in what we already know and then what we need to find. So in this case here, we mentioned that the sum of torque is at 0. And then the force produced by the muscle is not what's not given. So this is what we're going to be looking for today. But the distance is given, so we just plug that into 0.03 meters. And then we add that. And then the force of the weight would be at, we mentioned, negative 200 newtons. Times the distance that is from the axis of rotation, which is of the elbow, being at 0.25. So now we just do some math here. So we just do order of operations. So we just basically, first things foremost, we still keep this one since we don't have much to do here, but we can kind of like break it up here if that makes it more visual to see. Plus what we just did, so negative 200 newtons times 0.25 meters, that would give us negative 50 Newton meters. So now, since we want to kind of get force of the muscle by itself, we would just start by moving everything to the other side. So we would just basically subtract, or in this case, in this instance here, we would add actually 50 Newton meters to both sides, since we know that this one's at negative. So we would just add 50 Newton meters here. That would give us 50 Newton meters is equals to force of M times 0.03 meters of the distance. And now we just simply divide 0.03 to both sides. So, because remember, the end goal is to try to get the force of muscle by itself to find the answer. Once we do that, once we plug into our calculator, the 50 Newton meters over 0.03 meters would give us a final answer of the force being produced at the muscle, or aka the biceps brachii, would be 1,666.67 newtons. And that would be our answer and our walkthrough process to find for the muscle produced, or the force produced at the muscle, which in this case instance would be the biceps brachii. Now for question number 3, this is going to be kind of the same processes as question number 2. This one's asking us to maintain a static equilibrium. How much force must be produced by the biceps brachii attaching at 90 degrees to the radius of 0.045 meters from the center of rotation at the elbow joint to support a weight of 81 newtons held at the hand at 0.41 meters from the elbow joint. So don't freak out, this is just the exact same process as we would do as the above question number 2. The only difference is the wording, as you can see here. But this one, if you can kind of think of it, is much more simplified, and it's already given to what we already want to find. So if anything, this one should be relatively more easy to know. So let's always just start by what's known. So in this case here, it's the same process. It's asking us how much force is produced by the biceps brachii, so we know we're going to be looking for the exact same thing as question number 2. So let's start off with what's known. So we know that obviously we don't have the force of the muscle, so this is what we're going to be finding here today. But we do have the distance from the radius, from the center of rotation, which is at 0.045 meters. And then in this case here, we're also giving the force of the supporting weight, which is at, I believe, 81 newtons. And then we're also giving the distance from the elbow joint, which is our center of rotation of the weight. Which is at 0.41 meters. Sorry, this is wrong. This is distance of meters. Apologies. And then also, since we're looking for the sum, this one is going to be the same thing. The sum of this would just be at 0, since we're still talking about that static equilibrium. But in this case here, it's already worded for us. So if we know it's in static equilibrium, we know the sum of all torques must equal at 0. So same process, we just go ahead and plug this into our formula. So that would be 0 is equal to force of the muscle, which we aren't given here, but we already know this is what we're going to be looking for here today, times 0.045 meters plus, and then always remember, I totally forgot to mention that our force of the weight, it would be negative 81. Like I mentioned earlier, it's negative 81 because we can amplify that the force of the weight is acting downwards, so against us here. So we just put 81 newtons times the distance from it, so 0.41 meters. So now we just do our simple math here. So we just go ahead and do 0 is equal to, just keep this here, since we haven't really touched this much. But this one we can go ahead and once we plug into our calculator, we would get negative 33.21 Newton meters. So now we just go ahead and same thing, move to the other side to try to get force of muscle by itself. And this would just cancel out, and this would give us 33.2 Newton meters is equals to force of muscles times 0.045 meters, so it's a distance. So in this case here, we just kind of remember we're trying to get the force produced at the biceps brachii, so we just go ahead and just divide 0.045 meters, which is the distance from the elbow to the other side. Once we plug that into our calculator, we would just get the final answer of the force produced at the biceps brachii, so our muscle, would be equivalent to 738 newtons. Like I mentioned, same exact process as the above one, just the wording of the question is different, but just look out for those keynotes that we mentioned earlier. All right, so the last question, question number 4, it's asking us, SpongeBob and Patrick push on opposite sides of a swinging door. If SpongeBob exerts a force of 40 newtons at a perpendicular distance of 20 centimeters from the hinge, and Patrick exerts a force of 30 newtons in the opposite direction at a perpendicular distance of 25 centimeters from the hinge, what is the resultant torque acting at the hinge, and which way will the door swing? So in this case here, on conclusion, we're just finding what the total net torque is, and then in which direction will it swing. Will it swing in Patrick's direction, or will it swing in SpongeBob's direction here as well? So like always, let's just always start off with what's given and what's known. So let's just write down on the side. So we can go ahead and just start off by let's just start with SpongeBob. So in SpongeBob's case here, we know that he exerts a force of 40 newtons. And then what's the distance from the radius from SpongeBob? This one is 20 centimeters. But remember, in this case here, we always want to convert centimeters into meters. We want to be at that meter. So 20 centimeters in meters would just be 0.220 meters, if you can say. Now, what's Patrick's force? So in this Patrick's force here, so Patrick's force would be, I believe, was 30. And then the distance from the hinge for him was 25 centimeters. So if we just convert that to meters, that would be 0.25 meters. And also another thing that I forgot to highlight is that we want to make sure that at least one of them, this one right here, is going to be in the negative. So in this case here, we put negative here just because we know that the force is acting upon the opposite direction of it. So that way we know in which direction. So if we keep it at positive, we're not going to know in which direction we're going to be looking into. So we want to keep those separate so we know in which direction at the end it goes towards to. So the formula for total net torque, as we know, total net torque would just be equal to the force and distance of both individuals, or however many you have here. So in this case here, we have SpongeBob's at 40 newtons times the distance, so 0.20 meters. And then we just add whatever that is towards this one. So Patrick's would be at 30 newtons times 0.25 meters. So once we plug those in, we just make our math calculations here. 0.2 meters times 40 would give us 8 Newton meters. And then once we plug this negative 30 newtons times 0.25 meters, that would give us equivalent to negative 7.5 Newton meters. And then once we plug this into our calculations, 8 minus 7.5 Newton meters would just give us 0.5 Newton meters. Since we do see, remember, the negative is also, like, that's why I wanted to emphasize negative. Since we do see the total net torque being at a positive direction, we can amplify that, since we know that we kept SpongeBob's total net torque and all that on a positive. Since we see this answer correlating it to being positive, we can just infer from this case here. We know that the direction will be pushed towards SpongeBob. So in this case here, total net torque was 0.5 Newton meters in the direction that SpongeBob pushes it. So that would be, so let's just write this down. 0.5 Newton meters in the direction. That SpongeBob pushes. So that would be our answer for question number 4. This one's relatively easy. This one's just finding our total net torque and then just basically seeing in which side, positive or negative. So if this case here, if it was negative 0.5, we would have known that it would be in Patrick's direction. But in this case, since we know that we inferred that, is pushing, that is going towards the side that SpongeBob pushes. So that is the answer for question number 4. Hopefully this walkthrough was nice and clear for you guys to understand. Like always, if you have any questions, feel free to contact me. Have a good day.